axis. So you get an absolutely, it's black, jet black. I wanted to just show you that because it's kind of neat. She's not here, so we'll just move on. Now, getting back to the waveguide, I started going through the waveguide equation with you, and I was talking about TM. Y'all follow me on this, guys? I didn't assign any homework. I will tonight. But I wanted to go through and start sort of recapping because it's been a while. This is going to be for a waveguide. And this is going to be for TM polarization. That's transverse magnetic. And that means after you go through the equations, now I'm going to just put this down. You don't need to write it, but I need to get some, I have to have you have some perspective where we came from. Normally you start with curl of H is equal to sigma plus j omega epsilon times E, and then you get curl of E right here is equal to minus j omega times mu times H. These are the two equations we used to talk about. When we talk about a waveguide, inside a waveguide it has dimension A, vertical dimension B. This can be the x-axis. This can be the y-axis. And the direction of propagation will be z. That's just the cross-section of the guide. They're good conductors. There's a couple things that are apparent when you have these two equations. First, if these two equations pertain to material inside the guide, it's almost always got a sigma of 0. It's always very low loss. And in general, it is lossless for all intents and purposes. All right. That means these two equations then become curl of H is equal to j omega epsilon times E, and curl of E is equal to minus j omega mu times H. You get one equation taking curl of E is equal to minus j omega mu times curl of H, 4 times j omega epsilon E. Comes down and break that up as gradient of divergence of E minus del squared of E is equal to, and this becomes j times j is minus 1, times a minus is going to be plus 1, so you get omega squared mu epsilon times E right here. And at that point, you make the assumption that it's charge-free, or div E equals 0, which is equal to rho V over epsilon. So you get an equation where you have del squared of E, and then it's going to be plus omega squared mu epsilon E is equal to 0. And at this point, you don't have to worry about getting there, but you all remember how I got there. I'm going through this kind of quick, just bringing you up to speed, reminding you what we did. Now, for that equation, in general, the E field has 3 components, and we needed the del squared operator. Those are 3 derivatives with respect, second order derivatives with respect to x, y, and z, and in general, you would have 9 terms for that del squared operator operating on the E field. That's a lot. We can't do that. So with a waveguide, what you're going to do is take a look at that differential equation for one particular E field polarization, and that's the E field in the z direction. That's how come it's TM. Transverse magnetic means HZ equals 0. There is no magnetic field in the H direction, or in the Z direction, pardon me. There's only an electric field. This equation becomes del squared of EZ, right there, plus omega squared mu epsilon E equals 0. Y'all remember me doing something like this? How many do, out of curiosity? All right. I know I was online doing this, and I could not tell how well you could see what I was writing or not, but I did this, if you recall this. All right, I was trying to show you this. It's in his book. At this point right here, now we're only looking at the EZ component, so this becomes second derivative of EZ with respect to x squared, plus second derivative of EZ with respect to y squared, plus second derivative of EZ with respect to z squared, plus omega squared mu epsilon EZ equals 0. Now at this point I'm going to ask a question. Do you remember what my next step was to solve it? This is sort of the defining thing that you should know. At least you should, if you're ever asked this, make sure you have the correct response. Anybody? At all? There was something that I did. It was called separation of variables. Now I assumed you could use separation of variables, so I said EZ is just a function of x. They usually put a capital X of x, because that means it's a function of x, just a function of y, and just a function of z. All right, that's an assumption. We'll see if it bears out when we actually do this. So if I put this in here, that means I have a double derivative on x. The way it's usually rendered is just x double prime times y times z. Those are the functional forms of x, y, and z. Plus, then it's going to be x times y double prime times z plus x times y times z double prime plus, and here I'm going to call this beta unguided squared equal to omega squared into epsilon. That's consistent with his book. Beta is, of course, beta, and sub u, it means it's unguided. It's the same beta for free space. It's just equal to omega times square root of mu epsilon, or beta unguided squared would be omega squared mu epsilon. So I put that there, and then it's times x, y, z equals 0. Now the next step is divide everything on that equation by the functional form x, y, and z. Remember, capital X of x is just a function of x, but we don't know what it is yet. Capital Y of y is just a function of y. When you do this, it comes down to this. You get x double prime over x plus y double prime over y plus z double prime over z. And then it's plus beta unguided squared equals 0. That's what you're going to get. Now this is important. Try to appreciate this. This is x double prime, double derivatives, two derivatives on whatever x is, whatever the functional form is, divided by the functional form. And if we're adding to it something that's just a function of y, and something that's just a function of z, plus a constant, always 0, has to be. The only possible way that they can work is if x double prime over x, y double prime over y, and z double prime over z are constants. Y'all follow me on that? If they work, if you moved around, changed the position of x, if it changed the value of this, then if these two didn't move at all, it would not be equal to 0. Y'all follow me? So that's the idea behind this. And what they'll do is they'll say x double prime over x is going to be some constant. We call it minus beta x squared. That's consistent with Wentworth's book. It doesn't matter what you call it, but I'm trying to stay consistent with his book. You'll take y double prime over y minus beta y squared. Now, Wentworth's book does this different than I'm going to. When I have z double prime over z, I call that minus beta z squared. Wentworth's book just calls that minus beta squared. He drops the z, because Dr. Wentworth's book, beta to him is beta that has to do with propagation in the media or in the guide. So this is actually beta sub z, but he doesn't put the sub z on it. I do. That's the only difference. You get these three equations, and remember, these are constants, right? They're always going to be constant. When you do that, we'll solve one of them. And I've solved these before, but I'm just going to solve the first one, and we'll get the we get this from the boundary values that are allowable. When you take a look at that first equation, the x one, I have second derivative of x with respect to x squared, right there. And it's going to be plus beta x squared times x equals 0. The only thing I've done here is this. Multiply both sides by x, then take this to that side. That's what you get. Can you all see this right here, class? When you do that, the next thing I'm going to do by the way, is there any airflow out of there? Can you see if you can turn that on? Is there anything over there that you can adjust to turn on the air conditioning?
It's under 75 right now.
Turn it down. What I'm trying to do is get airflow in here, because I think one of the reasons I got this thing was there was an insufficient amount of airflow in here on Friday. I mean, I don't know who was sick with it, but the thing was staying. Is any airflow coming down?
Just try to turn it down to 72.
Just leave it at 72, see if something happens. Oh, I hear a sound. Yeah, remind me always to make sure there's some airflow in this room. Leave that door open. Okay, back to this thing right here. Now, this is a standard second order homogeneous equation. How many remember solving these things back in the day? Okay, what did you do? If you're in signals and systems, how would you solve something like that? Say it was a time derivative, not spatial derivative. Anybody? Laplace transforms, right? Sure. We're engineers, we would do that. We could do it that way. Back in the day when you had your math courses, how did you solve it? Integrating factor, do you remember that? And you also knew the general form of the solution would be e to some constant lambda times the spatial variable, which would be x. Do you remember that? And then you would solve for lambda. Lambda would be equal to actually beta x in this one. So, make a long story short, no matter how you solve this, at the end of the day, the solutions that are possible for x are either going to be equal to a sine of beta x times x, or a cosine of beta x times x, or possibly e to the plus or minus j beta x times x. It's one of those three. Now, the way we determine what it is because that x right there is multiplied by y and z and proportional to ez, right? So we know about ez. Ez is going to be the electric field that's really perpendicular coming out of the void. If that's x and that's y, z's out of the void. Well, ez would be the tangent component of the electric field on the walls of the waveguide, correct, class? And it has to be zero. Y'all with me? The tangent value of the electric field on any conductor is zero by definition, or else it's not a good conductor. That's just fundamental. So the way we get this is we take a look at the various solutions, but for this one, only the sine of beta x times x guarantee the zero here at that point when x is zero. If we try to cosine is zero is 1. So the coefficient of the cosine here would have to be 0 to maintain that, which means you'd have a null field. At the end of the day, it means our x of x will have the form of some constant, you can call it E0 if you want, times the sine of beta x times x. Now that's going to be the form. Do you remember what the next step was to determine beta x? Y'all realize that works when x is 0, right? It is 0. Where else is the E field 0? At x equals a, right? So that means the sine E0 times the sine of beta x times a has to be 0, right? All right. So this argument is not 0 any longer, right? But when is the sine 0? When the argument is sine of x, when x is 0, when x is pi, when x is 2 pi, when x is n plus or minus n pi, right? So now what you can do is say this. You know that beta x times a has to be equal to m pi, and that means beta x is equal to m pi over a. That's the end of the story on that one. And m has to be an integer, but it can be a negative integer. Y'all follow me? So now we've got beta x. In a very similar fashion, we can get, when we do this thing right here, and we put it for y, we'll get the y variation. It'll have the same possible forms, either sine, cosine, or an exponential, and it has to be the sine for the same reason. The E field has to be 0 at the boundaries. And let me just do that over here. So at the end of the day, what you're going to find out up here for EZ, you're going to find out that EZ is going to have this form. It's gonna be some E naught, that's just a scalar value. It's gonna be the sine of m pi over a times x. Then it's gonna be the sine of n pi over b times y. And it will be E, now the Z form, I didn't actually do the, right here, when I solve for this one, here, it doesn't go to zero ever. That's the propagational direction of the E field. So for EZ, now we get the exponential term. We're going to get e to the minus j beta z times z. And that will be the electric field form for the TM mode. That's the electric field in the z direction. It's real important to notice this. I got to make a few comments about this. We'll get beta z in 1 second. Now listen, this is important. Remember, this is TM mode in a waveguide. When you take a look at this, the smallest possible value for M and N, where a mode can actually propagate, has to be for M equal 1, N equal 1. And here's why. What if M was 0? What is the sign of 0? 0, isn't it? Sign of 0 is 0. It means the whole thing's 0. Nothing's there. There is no field if M is 0. What if N is 0? Same thing, right? So the lowest possible mode, for TM is M equal 1, N equal 1. Now, you'll learn more about that later. You're going to see for the TE case, it's the 1-0 mode. You can have one of the two be equal to 0, but there won't be sines, there'll be cosines, and that comes in a bit. Y'all with me? Now, what we're really after next is this beta z. And here, I'm gonna use this board and this board right here to show you how it's done. So, when we were doing all that separation of variables, we had minus beta x squared minus beta y squared minus beta z squared plus beta unguided squared equals 0. Whether you know it or not, that's from separation of variables. We came down to that. When you take a look at beta z, well, beta z is equal to square root of, and now I can take a look at this. That's actually equal to beta unguided squared right there. And it's going to be minus beta x squared minus beta y squared. Can y'all follow me? I've just rearranged things and put the square root there. Now, beta unguided is omega squared, or beta unguided squared is omega squared mu epsilon. Beta x is m pi over a, we just found it, squared. Beta y is n pi over b. So now I say that beta z is equal to some governor said. This is one of these spam things I'm getting for elections. Alright, come down here, and that becomes square root omega squared. Tell you what, I'm gonna do this. I'm not even gonna do that. I'll make it easier on both of us. I'm gonna leave it as that. And I'll say beta z squared is equal to omega squared mu epsilon minus m pi over a squared minus n pi over b squared. The only thing I'm doing, I'm saving myself some time on this one. Y'all follow me? I just put the variables in there. Now, with a waveguide, something I failed to say, a waveguide is a high-pass filter. The waveguide will not, it requires the frequency it's sited at to be beyond some threshold cutoff before anything can propagate. Y'all follow me, class? So it acts as a high-pass filter. There's some minimal frequency you have to be at before anything will propagate. And the way they find it out is they let beta z equals 0. So when beta z squared equals 0, we call this cutoff. Now, that means the propagation in the z direction, the actual beta value is 0. And what it really is suggesting is this. You know how I told you with waves in a waveguide, how they basically ricochet like this? That's how waveguides actually go. Well, when you have beta z equals 0, the wave is just bouncing up and down. There is absolutely nothing going down the waveguide. You all follow me? That's what beta z equals 0 means physically. When beta z equals 0, now we have omega squared mu epsilon. We call it omega sub c. That's the cutoff radial frequency, radian frequency. And I'll put it over here. So now I get omega c squared mu epsilon, that's this, and I'm going to set it equal to all this stuff, is equal to m pi over a squared plus n pi over b squared. Remember, omega c is the cutoff frequency in radians. Now, I'm going to rearrange this, and I'm going to let omega c be 2 pi fc. So omega c is 2 pi fc. That's the cutoff frequency I'm after. And when I do this, I find out that I have m pi over a squared plus n pi over b squared, square root of that. And then I take 1 over mu epsilon, right there, or I should say square root of mu epsilon, right there, and that's equal to 2 pi fc. Now just take a look at that for a second, make sure you agree with what I've done. I basically solved for omega c squared, then I took the square root of both sides to get omega c, and then I substituted in 2 pi fc for omega c. How many see this and understand what I've done? I'm not trying to do anything, I'm not trying to take too many steps before it, really frontward before I explain it. Then I simply divide by 2, so that means this becomes 1 over 2 square root of mu epsilon here, and then I divide everything by pi. You'll notice if I divide by pi on that side, it's really dividing inside that squaring operation, or inside the square root by pi squared, so it gets rid of these pi's. And that is the cutoff frequency. But you're going to notice this, the cutoff frequency is a function of m and n. Y'all follow me on this? Now this will be the cutoff frequency for both the TE and the TM modes. I'm just telling you, they are the same, the cutoff frequencies. For a TM mode, the lowest frequency you can drive a waveguide in the TM mode will be the 1-1 mode, when m is 1 and n is 1. Do y'all follow me on that? And you'll see when we do the TE mode, the lowest frequency is a 1 ohm. Yeah.
What are the M and N?
Integer values that indicate the mode number.
Is that just a given for the waveguide?
Yeah, well, it's dimensionally given by what? I mean, m and n are just integers. The thing that determines the frequency, if you look here, this is an actual frequency, right? So the thing that determines the actual frequencies are the dimensions a and b and the value of mu and epsilon inside the guide. Now let me give you some perspective on what, when they say a mode number, what that actually means. I could tell you to turn in your book, but I think I'm just going to show you this. If you look at a waveguide as such, do me a favor, don't write anything, just listen. Just listen, right? Remember the functional form of these things, either sines or cosines. In our case, they're sines, right? Both vertically, both for x and y. When you have a 1-1 mode, if you took a look at the intensity of the electric field, what you'd see in this direction, you get a sine wave that would basically show you the proportional magnitude of the E field as you move in this direction, the x-axis, and you would get a sine wave this way. Y'all with me? That would be the 1-1 modal pattern in the two directions. If you actually looked, took a snapshot in time and looked at the energy, what you'd see is you get contours of constant energy or power density that would be basically moving to be a single circle where the peak value would be right in the center. That's what the contours would look like. You've seen these things, topographical things, where you basically see a contour coming out like that. That's the 1-1 mode. This would be the 1-1 mode. Now, if you had the 2-1 mode, then you get this in terms of the energy. You get two relative peaks that way, one relative peak that way. You can almost see what's going to happen. Now you would have contours where you'd really have two centers, and you would have something like this. And eventually the thing would blend like this, but you basically are going to have two modal centers. That would be the 2-1 mode. 3-1 would be 3 in that direction, 1 in the other, and so forth. But the higher the mode number, the higher the frequency is to. Yeah.
So, in a waveguide, do we have any control over the mode, or
Yeah.
do they all kind
Yeah.
of?
Here's how you do it. Good question. So I'm going to jump ahead. So when we go through the TE mode, you're going to see that the lowest order mode that will propagate in a TE as a TE mode is the 1-0 mode. That is the lowest frequency period that will propagate. Now, what they'll do when they're driving a guide, and I'm just trying to be as honest with you as I can without getting too deep into the theory, what they'll do is cut a little hole in the guide. And they're going to drop an antenna in here, straight through, and the antenna will have a depth so it'll be impedance matched. This is way beyond what we can talk about here right now. You haven't even had an antenna here. Then when it's impedance matched and it's in the 1-0 mode, the lowest possible frequency will propagate in only that mode. And what will happen is, if it's a 1-0 mode, you'll basically get a sine wave variation in the x direction and no variation in the z direction, right? I mean, in the y direction, pardon me. So the wave will be propagating with that type of modal pattern. You're going to have to just go with me on this one. It'll take a while for you to get a real appreciation for it. Now, the next highest frequency that would propagate, remember, after we go just above where the 1-0 mode will propagate with this antenna in here, we're feeding with antenna energy, it'll be developed. And the best way to think about this, I like a mechanical analog. You know what a bell is, right? Think of the Liberty Bell. You hit it, you hear a ringing at a certain frequency, right? Well, with a waveguide, when you hit it, if you're below the cutoff frequency, it rings, but it dies out real quick. There's no propagation. When you're above the cutoff frequency, that mode will propagate. And until you get this thing driving at a frequency beyond the second mode that it can propagate, only the first mode will propagate. That's important. Now, the reason that's so very important is you only want to drive one mode. If you have two modes propagating, the energy or the velocity will be different for each mode. And some of the energy will be at one mode, some at the other, and you'll get garbage coming out. You'll get a garbled signal because it will not. You know what aliasing is for signals and systems? You ever hear something that's undersampled and try to try to recreate it? It's garbled, right? Same here. If you have more than one mode going down there, any of your communication information, all that, it's garbled. That's why they only want one mode. And it's almost always the one mode that's sent. More on that in a bit, but I'm just trying to give you perspective. You asked about modes. I hope that at least gives you a clue to what I'm talking about. All right. So anyway, back to this thing. This is the cutoff modes for the M and N. And it works for both TE and TM. So next, and I'm getting back to this beta Z business. All right. Let me try to do justice to this. You know, can use that camera back there or not. Huh?
You might be able to on the actual computer.
I don't know, I mean, I haven't looked at our videos lately. Anybody?
The angle is bad,
Huh?
for sure.
It's not quite as good as it was last year, we had it last year.
If we could use that camera,
We can use that one, that'd be sweet.
You probably can.
if we can get it to zoom in close enough.
Yeah, that's the other.
I don't see why we can't. They tell us to do everything possible to help the students, so. If we can use that camera, we will. Okay, back to this thing, back to beta Z. Y'all follow me with cutoff? So, it's important we get this. Now, back to beta Z. If you look at this, I can actually go ahead and I can say, well, my omega cutoff, mu epsilon, is equal to that. I can modify this, and here's what I can get. I can get beta Z itself equal to, let me show you where this is in the book, because some of you are going to have questions about this. Now, I'll level with you. A lot of this, first time you're introduced to it, it seems a little overwhelming. It really does. So, okay, if you look in your books at the bottom of page 389, that's where I was. I'm looking for a simplifier here. That's not what I. And then if you look at page 380, equation 7.11, star that equation. That's your go-to equation. You're going to see beta Z, Dr. Whitworth's book just calls it beta, equal to, and you'll have it as beta unguided, times the square root of 1 minus, and it'll be FC over F squared. Now I'm going to explain something to you in a second. Just write this down. What he's actually done is, if we take beta Z here, and we solve for just beta Z, we can manipulate this where we get a cutoff frequency. That's what this is right there. We can manipulate it into that form. Let me just do something here. I'm going to say now my beta Z, which is equal to beta, Whitworth's beta, is equal to beta unguided. Well, beta unguided is really omega times square root of mu epsilon, right? Just leave it as that. And then it's equal to something that normally is called K, and K is just equal to the square root of 1 minus FC over F squared. Now, I've got a few comments on this one. Now, this number K we're going to use all the time for waveguides. Remember, FC is a cutoff frequency. Remember what I told you. You have to be at a frequency above cutoff for propagation. Do y'all hear me? Now, look at this. This will always be less than 1 if it's propagated. Y'all follow me? If it was greater than 1, then this would be a negative number in here, and you would have an imaginary value for K, which is meaningless. Nothing propagates unless you're above cutoff. But what does this number K really give you? Well, the closer you get to cutoff frequency, the smaller that gets, and eventually it becomes 0 at cutoff. And it really is just a multiplier on beta, on the normal, unguided beta. If the wave was unconstrained in free space, that would be the beta that defining the number of radians per meter. Can y'all follow me, class, on that one? Some of it is a little tough to get a handle on right away. It'll take some time. But just try to appreciate this. This value of K is very useful. And the only thing they've done here, instead of writing this thing as such and manipulating it, they get rid of this geometric effect and they just call it FC. So they get rid of the cutoff frequency in terms of all this nonsense, and they just have a ratio of cutoff frequency to actual frequency. Y'all follow me, class? Yeah.
I'm still not really sure, like, what is K?
It's just a number. I mean, it has to do with how close you are to cutoff. When you think about this, if you're at a frequency 500 times cutoff, all right, it's about 1. I mean, 1 minus 1/500 squared is about 1. You all follow me, class? The closer you get to cutoff, the smaller that number gets. And when it's 0, I mean, at cutoff it's 0, and that's when nothing propagates. Yeah.
And so the closer it is to one, if that first term omega, that's in free space, the closer you are to one, the closer you kind of get to how we
Yes, yes. As k approaches 1, you basically have a wave that is like a free space wave. It is basically not even bouncing. It's basically just straight propagation. But that's down the line. Just hang with me, all right? So this is beta z. Now, one other thing I have to get into before I get to TM or the TE mode. There's a lot of mathematics that seem overwhelming, but here's the real deal. Once we get this form of the E field, EZ, now we can go back and use the curl equations. The curl of E is equal to just J omega epsilon, or curl of E is equal to minus J omega epsilon H. We can get the E field and the H field for all the other different field components, both X and Y. Do y'all follow me, class? And Z. We can get them through the curls. Whitworth's book does that, and this is one of these things that's a exercise sort of in bookkeeping. It's really, everybody has to do that usually at least once. He does it in the very beginning, I think, of the chapter. Yeah, he does it on page 386, 387 and all. You can do it if you want, but he lists all the electric fields and H fields for the different field components if you're in a TM mode, and he'll do the same for TE. But once you have this, you can get the others. Matter of fact, I'm going to show you how to get.
So we start out by assuming we're just looking at the Z direction of the E field.
We're only getting a
That-
component of the E field in Z direction. From this, though, you can
all
get
the
all
others,
the other
E
ones.
sub X, E sub Y, whatever.
That's, as a matter of fact, he does it in the book, but I'm going to show you some tricks where you don't have to go through the curl. Now, you know me, I'm not a curl guy. I do them if I have to, but I prefer to have simple stuff to get there, and we're going to do it now. That's what I'm going to show you. Now we're going to talk about the impedance of the waveguide for TM and how to get the field components without driving yourself nuts. I'll tell you nowadays, though, I'll tell you one thing. How many have heard of Mathematica? Anybody? All right. Mathematica is rather interesting. It will take, you can put any kind of equation in there you want, and if you want the derivative of it, it will do the derivative. And it will give you an output in a form that's latex friendly. You know what latex is? Anybody? It's all, when we published all our papers, we write them in latex, because it's perfect typesetting stuff and allow you to write all sorts of bizarre equations easily. But doing the math on a lot of stuff, especially when you're taking curl of curl and then a divergence of some Bessel functions, it's reams of paper. I cannot tell you how much paper I've gone through when I was doing these. Just derivatives, driving yourself nuts, trying to find an error. Well, Mathematica does it seamlessly. The physics community loves it. And if you ever have to do actual derivatives, where you have to work them out, we have very long equations, please consider using Mathematica. It does it, and it's seamless. And then you can get it and output in a form that's latex friendly, so you can put it right in your paper. Some of you will be doing PhDs in years to come. You'll thank me if you hear me now, because it works. It's amazing. And look, I don't like to spend a lot of time wasting just running through derivatives and stuff like this. I'll use the computer to do it if it's available. And Mathematica is really good on that. So it's something to consider. Anybody try MathCAD at all in here? All right. I showed you MathCAD, right? I'm telling you, you'll love it. You get through your homework so much faster. But it doesn't matter, you've got things to do. Back to this stuff. Now, write this down. This is important. This is the TM mode. All right? So the TM mode, it's defined by the E field is equal in the Z direction is equal to sum E naught times the sine of M pi over A times X, sine of N pi over B times Y, times E to the minus J beta, and I call it beta z times z. Now that's for a forward propagating wave. That's the first, it's important. Lowest mode is m equal 1, n equal 1. Has to be at least that or greater. M and n both have to be at least 1. Alright? After that, cutoff frequency is the same as everything else. The cutoff frequency for the M-N mode is equal to 1 over 2 square root of mu epsilon, square root of M over A squared plus N over B squared. Now, beta in the z direction is beta unguided times k, where k is equal to the square root 1 minus fc over f squared. We've got beta z, and finally, I'll put it over here, the impedance of the waveguide in the TM mode is equal to just eta, where eta is equal to square root of mu over epsilon times k. So that's why this k is so important. Now that's the impedance. So if you wanted the ratio of EX to HY, or the ratio of EY to HX, it would be equal to ZTM, right there. Can you all follow me on this, class? That's the waveguide impedance. This is 120 pi usually, if it's air-filled, but it would be that times mu relative over epsilon relative if it wasn't air-filled. Follow me, class? Can you all see it back there in the far back? All right. I'm just trying to summarize. This is what you need to know for TV. Now, something else, and I'll put it over here. Well, I mean, these are the important facts. The next thing you need is the phase velocity. Well, phase velocity, V phase, is omega over beta, isn't it, class? I mean, that's the definition. Think about it. So this is the beta z, actually. So this is going to be equal to omega over, and this would be beta unguided first, so it would be omega times square root of mu epsilon times the square root of, and I'll just put in k here. It's 1 minus fc over f squared. Now, one thing you see is the omegas cancel. I get 1 over, this way, 1 over the square root of mu epsilon, and it's divided by k, right? Now I'm putting that k in here. I have a couple of comments. I want to make sure you see this. This is phase velocity. Remember how I told you phase velocity has nothing to do with energy, right? It has to do with the phase, or like an intersecting point on a boundary, how fast that intersecting point moves. What is 1 over the square root of mu epsilon if we were in free space? Speed of light. Over k. Well, I'll put this down. Square root of 1 minus fc over f squared. That thing, as you get closer and closer to cutoff, the phase velocity is getting closer and closer to infinity. Do you all see that? And in general, it goes to infinity when you are at cutoff mode. Now, remember what I told you about phase, how it's that, it's really like a point of intersection of a wave on a surface. And the way I always do it is, if you think about this as like a beach or something like that, and I try to do it, building really an analogy in the physical world that you can observe. If you have a wave that's coming at an angle, going with velocity v, and you look at this point, if it moves a little further down there, this point will move. There'll be a certain distance variation at a given time this way, and a certain distance variation this way. This will be greater. When that wave is coming in almost parallel to here, Then the intersecting point, if you take point one, let this go a certain distance for a differential amount of time. Now the intersecting point here would have traveled a much greater distance. That intersecting point, think about like where the wave breaks on the shoreline. That thing can move much faster than the speed of light. Nothing's really moving that fast. It's simply a point where they call it a phase point, all right? Nothing is really physically moving. This is the phase velocity. That's exactly what it is. It's the intersecting point on the wall of constant phase, how fast it's moving. The velocity of energy, or the group velocity, I'll call it V group 2, is equal to really C, or it's equal to 1 over the square root of mu epsilon, and it's times 1 minus FC over F squared. Now that's the one you pay attention to, because that can never be faster than the speed of light. And it will always be less than the speed of light. And it will approach the speed of light as the value of F goes to infinity. Y'all follow me on that, class? So this is the velocity of energy. Keep that in mind always. That's the important one. All right. So I'm trying to summarize the TE cases. I didn't actually. I can do the curl equation, from there get the A fields and stuff from E field.
Where, you don't have to go through it right, but where do you start to get the velocity of the energy population? You start from like 17 or something like that?
At a constant frequency, you can go ahead and just get Newton's point vector to get it. I think that would be the easiest, but let me talk to you after class about this. Let me do one last thing, class. I didn't get through the TE mode. I'm going to ask you to read through that. You're going to find exactly what I did today is going to be there for the TE mode. There's one difference. That form up here for the E field will have cosine, not sines. All right? And we'll do that next time. I'm going to give you some homework, and we'll talk about the homework. So, logical questions are quiz Friday. Answer, no. I haven't had enough time. We may do one on Monday. I'm just telling you. I'm trying to keep this class up to date. All right. See you on Friday.
I'm not sure whether or not this is a typo. It has for names attached to TE, and then for this, is this supposed to be TE?
Yeah. And the reason is because that's multiplied. That's remind me to talk about
multiple